Okay, so I'm honored to introduce the next speaker, Professor Weiping ZHANG from Cheng Institute of Mathematics, and he's going to talk about deformed Dirac operators and scalar curvature.
So thank you very much. First of all, I would like to thank the organizers for the kind invitation. It's a big honor for me to be able to speak in this conference dedicated to Professor Gang Tian, who helped me a lot in my career. So in this talk, I will describe, okay. So as we know that Dirac operators as well as the deformations have played important roles in many problems in geometry and topology. So we will describe some of these applications concerning scalar curvature in this talk. So indeed, it turns out that the Dirac operator goes far back to the 1846 when Hamilton discovered quaternion. He already wrote this formula that the square of the first order operator equal to the Laplacian. And many years later, Dirac, indeed Hamilton claimed when he wrote this formula, claimed that it will be play important roles in mathematics and physics. It turns out that what he said is very correct. So many years later, Dirac discovered the following formula, where gamma I is the so-called Pauli matrices verifying the so-called Clifford relations. And then to 1986, Tian and Singer in their road to discover the index theorem, they construct the Dirac operator on curved manifold, so on spin manifolds. And we need a spin structure. So now we started with this Tian-Singer's Dirac operator. So we take an even dimensional spin manifold, a closed, also give a metric, a Riemannian spin manifold, and denote nabla Tm the received connection and Rtm the curvature. Then with this metric and the spin structure, we can construct this bundle of spinors. In the even dimension case, the spinor bundle is the emission bundle of emission vector bundle. It had the mixed splitting to the positive spinor bundle and the negative spinor bundle, and it carries naturally emission connection induced by the received connection. In the general, that we also tested the emission vector bundle E over it. We assume it carries the emission connection with lambda E, and Re denote the curvature. Then the Tian-Singer's Dirac operator can be defined by this formula. Here, C indicates that the Clifford action acting on the spinor bundle, and EI is the local orthonormal basis. And since this sum does not depend on the choice of the local orthonormal basis, so this is a well-defined global operator acting on the spinor bundle twisted with coefficient E. And then with this splitting, the Dirac operator has a plus and minus splitting, which D plus maps from this plus to this minus. And then we have an index which is equal to the dimension of the kernel. Sorry, I missed the dimension symbol, and minus the dimension of the kernel of D minus, which is indeed the dimension of the co-kernel of the D plus. And a Tian-Singer index theorem says that this analytically defined index, which is indeed is a topological invariant, can be indeed be expressed by this topological characteristic class evaluated on M. And here, by the Chen-Wei theory, the A hat and the Chen character can be expressed using curvature forms in this way. Here, I would mention that the spin condition is essential. For example, for CP2, the A hat genus, which means the integration if we take the E, the trivial complex line bundle, then the A hat genus is equal to minus 1 over 8 is not an integer. So the spin condition is important, essential for the Dirac operator. As an early application, Lichnowitz says that the square of the Dirac operator indeed equal to the Buchner Laplacian plus the scalar curvature over 4. So here the scalar curvature appear. The Bochner Laplacian turns out is negative, and so if the scalar curvature is positive, then the D square will be invertible, and then the kernel of D will be 0, and the index of D will be 0. So by a Tersinger index theorem, the A hat genus would be 0. So Lichner's conclusive theorem that on a spin manifold, if a spin manifold carries a metric of positive scalar curvature, then the topological A hat genus should be 0. So this is, in many sense, this is the first topological abstraction to the existence of a metric of positive scalar curvature. So it's since the scalar curvature is one of the basic invariant, so it's a natural question, that important question is that whether on a manifold there exists a Riemannian metric of positive scalar curvature. And this question arises a lot of studies. So for example, Gromov and Lawson proved in 1980 that every simply connected non-spin closed manifold of dimension larger or equal to 5 indeed carries a metric of positive scalar curvature. Here, the condition is non-spin, simply connected. And on the other hand, Stolz proved that a simply connected spin manifold of dimension larger or equal to 5 carries a metric of positive scalar curvature if and only if the so-called alpha m, that the Atiyah-Milner single alpha invariant, vanishes. And in dimension 4K, this alpha m indeed is the A hat genus. So for simply connected spin manifold, the A hat genus indeed give a perfect satisfied answer that whether a match on a simply connected if and only if this is obstruction. So you can see that for dimension larger or equal to 5 simply connected manifold, the existence of metric of positive scalar curvature, the question has a satisfied answer. It is characterized by this vanishing of this topological invariant alpha m. In dimension 4K is indeed the A hat genus. So then for the non-simply connected case, the simplest example for the non-simply connected manifolds are the torus. So here we have a famous theorem of Xun-Yao and Gromov-Lawson saying that there is no metric of positive scalar curvature on any torus. Xun-Yao first proved this result for dimension less than equal to 7 by using minimal surface method. And Gromov-Lawson later, since Tn is spin manifolds, so using Dirac operator and index theory to prove this. So there are usually two kinds of methods working on the problem of the scalar curvature, exists on positive scalar curvature. One is Xun-Yao's method, minimal surface method, and the other one is the index theoretical method initiated with Lichner's formula. And then Gromov-Lawson make very important contributions. And for us, in many cases, the deformed Dirac operator will be also play important roles. And the basic structure is indeed, algebra structure is indeed very simple. So on a spin manifold, instead of consider one coefficient bundle, we consider a Z2 graded emission vector bundle, that is Xi plus Xi minus R2 vector emission vector bundles carrying emission connections separately, and we assume for simplicity that we work on even dimensional spin manifold, Riemannian spin manifold. Then with this Z2 grading, we take V, a self-adjoint endomorphism of Xi by odd endomorphism. By odd, we mean that V exchanges Xi plus and Xi minus. Then since on the even dimensional spin manifold, the spinor bundle also carries the Z2 grading. So we take the graded tensor product with this C hat here. Then this operator is self-adjoint, but with the D plus and D minus, for example, D plus would be the positive part of this graded tensor product would be take this form, this S plus tensor Xi plus, then plus S minus tensor Xi minus. This will be the plus bundle of this graded tensor product. And here we have a minus bundle of this graded tensor product. So then the natural index to consider is of this D plus. Then with this endomorphism V, with this Dirac operator, then for any t in R, we can consider the deformation dt, which is the d plus tv, plus tv. Both are self-adjoint. And if we compute the square, as usual, we always compute the square. If you have a first order operator, self-adjoint operator, then it will take tautological take of this form. And here, the bracket is the Z2 graded bracket. This is dv plus vd, not dv minus vd. It's a Z2 graded commutator. And then since v is odd, it exchanges plus and minus. So this term will be a bounded term. This term was bounded term. So in many cases, the t square will dominate the coefficient of t. So we will take it as a later example, as now we take a concrete example. We assume now that the manifold is a complete manifold. The Riemannian metric is a complete. And then we assume it might be non-compact. And then we assume there's a compact subset K such that the order endomorphism V has the lower bound, the norm has a lower bound delta outside this compact set. That means near infinity V is invertible, has uniform invertibility. And we also assume V outside this compact subset identify the two vector bundle, meaning that it's a parallel with respect to this connection. Then with this term, with this condition, then the Dirac of the commutator will turn out to be 0. So then the dt square would equal to d square plus t square v square, and this is the negative. So if we have a v square have a lower bound delta, then this has a uniform positivity near infinity. Then with this, we can do this standard analysis. Then this dt square would be the dimension of the kernel, would be finite dimensional. That means it induces a Fredholm operator. Then you can, if you get a Fredholm operator, you can compute its index. And so the simple relative index is indeed for any t bigger than 0, then you get a Fredholm operator dt plus, and the index can be computed by this right-hand side. This right-hand side turns out is evaluation of non-compact manifold. But since outside the compact subset, these two vector bundles are identified. So indeed, if you use Chen-Wei integration, Chen-Wei form representative and integration, it's an integrate on a compact subset. So it's well-defined. And this index is indeed motivated by Gromov-Lawson's famous relative index theorem. So for Gromov-Lawson, they assume that the scalar curvature has a uniform positive lower bound near infinity, the outside the compact set. And then they also assume that the psi plus minus are trivial bundle identified outside this compact subset. Then by using Lichtenau's formula with this coefficient, the dt square would equal to the Laplacian plus scalar curvature and plus dv square. So since now the scalar curvature has uniform positive lower bound. So then here the t can be, if you even take t to 0, the dt square will still be uniform positive invertible outside the compact subset. And then in this case, you can take t equal to 0. You have a continuous family of Fredholm operator. The index does not change. And here now index turns out is Gromov-Lawson's relative index, the index d with psi positive coefficient, and both of these indexes are well defined under the condition that the scalar curvature has a uniform positive lower bound. And the right-hand side is exactly the same as this index. So this is Gromov-Lawson's famous relative index theorem, has played a very important role in their big paper. studying the existence of matrix of positive scalar curvature. For example, they introduce what we now call area enlargeable manifolds. So a Riemannian manifold is called area enlargeable if for any epsilon, any small epsilon positive number, there's a covering pi from m epsilon hat at the current space hat to m with a lifted metric. And on this covering manifold, there exists a smooth map F, mapping this covering to the standard unit sphere of the same dimension, and which is constant near infinity. That means it's constant outside the compact subset and of non-zero degree. And moreover, by area largeable means that for any two form on the sphere, unit sphere, the pullback two form under this covering, the norm with respect to the pullback metric is less than equal to epsilon times this the norm of the alpha on the unit sphere. That means if you push, if you push, then you push every region to the area at a two-dimensional region to a very small epsilon area with decrease to multiple of epsilon. Of course, when M is compact, this area enlargeability does not depend on the choice of the metric. But on the non-compact case, we usually call that area enlargeable Riemannian manifold. The typical example is the torus, which we already mentioned, that Shungyao and Gromov-Lawson's result. Also, if you have a closed area enlargeable manifold, and also N is any other closed manifold of the same dimension, then the connect sum is still area enlargeable. So Gromov-Lawson, using the index theory, proved a very famous theorem, says that if M is a Riemannian manifold is complete spin, here for Dirac operator, spin condition is essential, area enlargeable manifold, then the scalar curvature of this metric cannot have a uniform positive lower bound. That means the infimum of the scalar curvature should be less than equal to zero. And this is so there is a proof by using using their relative index theorem. It's just a one-page proof. I will not repeat for the time reason. They're using the relative index can prove that any area enlargeable complete manifold, spin manifold, cannot carry a metric of uniform positive lower bound. If the manifold is compact, then indeed they immediately get Shungyao and Gromov-Lawson's result, since the torus is area enlargeable. So they get the area enlargeable. So on the torus, there will be no metric of positive scalar curvature. Moreover, for any closed spin manifold, this connect sum is also area enlargeable, so cannot carry a metric of positive scalar curvature. And this is interesting because Lecomte, many years later, observed that such a property, that a closed manifold, if we connect sum with torus, cannot have a metric of positive scalar curvature. This property would imply the positive mass theorem for N, for this closed manifold. So Gromov-Lawson's result for any dimension already means that the positive mass theorem holds for any spin manifold. Of course, historically, it is Shungyao who first proved positive mass theorem for any closed manifold with dimension less than or equal to 7 using minimal hypersurface method. And Witten first proved for the spin case without using this connect sum property. And later, and more recently, Shungyao presented a proof of positive mass theorem for all closed manifold using generalizing their minimal hypersurface method. And on the Dirac operator side, that usually we need a spin condition. So it's always a question whether there will be direct Dirac operator proof for non-spin N. For example, for the simplest case, the T4 connects them with CP2. CP2 by Shungyao, it does not carry a metric positive scalar curvature, and And but for Dirac operators, I will come to this point in a moment. Then now I recall that the Gromov-Lawson proves that if you have a complete area enlargeable manifold, then the scalar curvature cannot have a uniform positive lower bound. But now with our new relative index, I just mentioned that for deformed Dirac operator, we do not need this uniform positivity of the scalar curvature near infinity. So when we ask that whether in this theorem that this inequality can be replaced by the strict inequality, and here there is no general answer for this question. But for the special case of the connect sum, we can prove the following. This is a joint work with Xiangsen Wang, that if you have a closed spin area enlargeable manifold, and then we take n here with spin manifold, but we do not assume it's compact. We can take a non-compact spin manifold. Then we do the connect sum. Our result says that there will be no complete metric of positive scalar curvature on this connect sum. If you use Gromov-Lawson's relative index, you can prove easily that there's no complete metric of uniform positive scalar curvature on this connect sum. But here we can improve it just without this uniform positivity. We prove this one. As a corollary, you can see that for any non-compact spin manifold, its connect sum with torus cannot carry a complete metric of positive scalar curvature. And this result is indeed recently of some interest when n equal to 3. This corollary is due to Yao and his corroborates Lesund, Unger, and Yao. And when the dimension is less than equal to 7, it was also proved by Chadoshi and Chao Li. And I was told that their method can be improved to n less than equal to 10. And also such a kind of result is closely related to the positive mass theorem in a non-compact setting. And for general non-spin case, of course, is still open. Now I come back to the question of the torus connection with the CP2. So now we consider a spin C manifold. What is a spin C manifold? Spin C manifold is a generalization of a spin manifold. So it means that there is a complex line bundle over the manifold, such that the first term class is equal to W2 second Stephen class in this cohomology with Z2. So if W2 equal to 0, then this is spin manifold. So if there's a line bundle so with the W2 is more to equal to a first term class of a line bundle, it is a spin C manifold. So the complex line bundle, you can identify it with the Euclidean rank 2 vector bundle. So you can take a transversal section. Then transversal section, the 0 set will be a codimension 2 closed submanifold. Codimension closed submanifold. So then you take any psi or Z2 greater bundle in our abstract setting for Z2 great for deformed Dirac operator. We take the connection and we take the curvature. Then we also assume there is an odd endomorphism V of this twisted Z2 greater bundle, such that odd means V exchanges Xi plus Xi minus, as we said. But we assume that V is invertible on this submanifold on this 0 set of the transversal section. Then we assume that there is a metric on the manifold such that its scalar curvature verifies that its scalar curvature dominates the curvature of this twisted bundle. Curvature dominates with this twisted bundle. Then our theorem would say that under this assumption, we have this spin C in Dirac index of spin C Dirac operator equal to 0. Here this the Chen character is Z2 graded Chen character equal to the Chen character of Xi plus minus the Chen character of psi minus the Z2 greater than character. So if the manifold is spin, then we can take this line bundle to be trivial line bundle, and then sigma the take transversal section without zero, then the submanifold will equal to zero. Then you can also take psi as a trivial bundle. Then this condition is just the positivity of the scalar curvature, and then you recover the Lichtenauer vanishing theorem on spin manifold. So this theorem, tautologically, you can view it as a generalization to spin C manifold of this Lichtenauer vanishing theorem. An interesting corollary is that if we assume this is correct, then using some trick, you can prove that if M is a closed spin area enlargeable manifold, and N is any closed spin C manifold, then the connect sum is a spin C manifold, cannot carry a metric of positive scalar curvature. So curvature. If we take M equal to torus, then we recover in the special case, Xiong-Yao's theorem says that for any closed spin C manifold, there is no metric of positive scalar curvature on this torus, on this connect sum. In particular, one gets an index theoretic proof of the fact that the CP2 connect sum with T4 indeed does not carry a metric of positive scalar curvature. Originally, it was proved by minimal surface method, but with this generalized Lichtenauer formula, one can give an index theoretical proof of this the result. Let me just a few minutes. Let me outline what's the basic setting, the proof. So here we consider the spin C Dirac operator. Spin C Dirac operator twisted with this bundle psi. And then here, the spinor bundle here, since we have a line bundle here, the spinor bundle here is called spin associated with the spin C spinor bundle. Locally, it can be written as a spinor bundle tenses the square root of this line bundle. Of both spinor bundle and square root do not define globally, but their product, tensor product defined globally. So if we work on this operator, then the Lichtenauer formula will be expressed as a curvature, scalar curvature as usual, plus this curvature term. Here, this term, this scalar curvature term plus this the last term curvature term. This term, by our definition, this will be this sum. This sum will be positive. So if the curvature involving the line bundle is zero, then you can get what you want. But indeed, but usually for the spin C case, this line bundle is non-trivial. So this curvature will cause trouble. But the simple observation is that the zero set of the transversal section of the line bundle sigma is a codimension 2 submanifold, is indeed an obstruction of the manifold to be spin. So if you cut out this submanifold, then this one is spin. Or if you cut out the double neighborhood of this sigma, then the manifold rest of manifold with boundary, the spin manifold is boundary. And moreover, the line bundle restricted to this manifold's boundary will be a trivial bundle, because all the singular, because it has a transversal section, nowhere zero transversal section. So it's a trivial bundle. So that means outside of this sigma, you can view the spin C Dirac operator somehow as a usual spin Dirac operator with trivial coefficient. And then when localize the problem near this submanifold sigma, near that, and here our assumption is that we have invertible V. Invertible V here will play a role to deal with this question near the sigma. And needless to say that we need kind of some deformation using this V of the Dirac operator to do it. So the deformed Dirac operator will still play an essential role in this setting. And unfortunately, that here the spin C condition is essential. So the open question remains, how to deal with the general non-spin manifold. So in general non-spin manifold abstraction, sigma should be is indeed two dimension, but it will be non-smooth. It could admit singularity. So this I'm not. It remains how to do this some manifold with singularity to deform Dirac operator. This is still remains a question. I cannot do this. This is left open here. So with this, I would like to say that time is up. I would like to say happy birthday, Professor Tian. I stop here.
Thank you very much. Any questions and comment?
So for a spin C manifold, you assuming you can do this non-existence positive scalar curvature. So you need this curvature condition. So for example, if you assume the positive curvature, you still need to find the Cassini, right? The bundle so that the curvature is not.
Yeah. So in general, so this condition is condition here because in general, if you working on connect sum, because you have an error in larger case, you map to a sphere. So you map to a sphere. Then the enlargeability, if you take an enlargeability here, then you pull back the bundle, pull back the bundle on the sphere, then its curvature will be very small.
Okay, so you can
Yeah.
somehow by enlarge things. So
Yeah,
also you say in the last page you say it's this you for sigma this where the support spin and where the support to a Whitley class. So you say you can do for smooth case or you
in the spin case, if sigma is smooth, it's equivalent to saying that the manifold is spin. So because if we smooth orientable manifold due L to the second stable Whitley class, then it generates a Z cohomology.
Maybe I missed the point. X is sigma is 0 for X. X is some
X
vector
is
field.
transversal section of the line bundle.
Oh, okay.
That means the cohomology of this sigma is due L to the
Chen class.
stable class.
Any more questions?
So this gives a different proof from the Shen-Yao proof?
Yes, only for spin C manifold.
I see. And
For
they don't
positive
assume
mass,
that?
you mean? No.
Yeah, for the positive mass theorem, for example, for spin C manifold.
So they don't need to assume that?
They do not assume their proof, if correct, works for all closed manifold.
I see. But this is like completely different proof.
That can be different. This is using Dirac operator.
So you for this Xiong case, they use a hypersurface. You list the two papers. I thought that they posted this proof in 2017, but there's also
then later they publish in the Surveys in Differential Geometry in 2021, I think.
Wow. Okay, so this is a revised version or for the
I
previous
think
one?
it's exactly the same version.
Okay, so it's just published in the 21. It's the same paper.
Yes, the preprint is in 2017.
If no more questions, let's thank Professor Zhang again.
Thank you.